Sir, Mr. Angit sir from CMTI, requesting Angit sir, resource person from CATI. Sir, shall we start, sir? Angit sir.
Yes, sir. Hello. Just give me about a minute and I'll be ready to start, sir. Is that okay? Yes, sir. Hello. Just give me about a minute and I'll be ready to start. Is that okay?
Sir, thank you, sir. Angit sir, let me start, sir.
Yes, sir. Please go ahead, sir.
Okay. So now let me, good afternoon to one and all present here, to all the participants, welcome back. Now let me introduce the resource person, Mr. Angit Krishna sir, scientist from CMTI, Bangalore. So he has done Master Technology from National Institute of Technology, Karnataka, Surathkal, in Design and Precision Engineering. He has developed micro 3D printing machines, biosensor heads, processes for focused ion beam milling for nano machining, for super hard materials like a diamond, for ultra precision machining applications. He has filed many patents and has about 8 technologies with 3 qualified deployable products. He has published more than 22 articles in various journals and conferences and guided more than 12 students for their research work from IITs, NITs, and other colleges. Now I request our resource person to proceed with the session, sir. Requesting, sir.
Good afternoon to all of you. Thank you for tuning in into this session. I'm really grateful to SVEC College for inviting me for this talk once again. So many of you might have attended my talk previously also, so it's not going to be very different except for the fact that there are going to be these few changes. So let me just put my screen for share my screen.
Excuse me, sir. I request all the participants to mute your mic and switch off your camera.
Please hold on. I am not able to get this, unfortunately. Just a second.
Okay, okay. Sir.
Please hold on. I am not able to get this, unfortunately. Right. Are you able to see my screen? Because I don't get feedback, unfortunately, on.
No, sir, not yet, sir.
Not yet? Okay.
Nice.
Are you able to see my screen? Because I don't get feedback, unfortunately, on.
No, sir, not yet.
Now is it visible?
No, sir.
Okay. Let me see. It's not allowing me to present now, unfortunately. Can you help me out, sir?
Yes, sir. Yes, sir.
Yeah. Is it audible? Is it now seen on your screens?
No, sir. I think we will see here. We have to see here presenting now with your name or with your screen, sir, but it is not visible.
Here it's grayed out in mine.
Okay.
It's not allowing me to click here.
Sir, Rajesh, sir.
Sir, I am available, sir.
Is there anything sir has to do, sir?
Sir, actually, I have switch off my presentation. So
Okay,
right now, you
okay,
can
sir.
present, sir. Ankit, sir, I think you can go ahead, sir.
No, I mean, actually, I'm having a problem. The present now here is actually grayed out. So,
Grayed out, huh?
yeah. Is it possible for you to activate?
Sir, I think there is no other options, no?
Okay, I'll do one thing in that case. Can I just close this and again I'll rejoin in a minute?
That will be better, sir. Better.
Yes, sir. Yes, sir. Yes, sir. Please.
Ankit, sir, so go ahead with your mail ID, sir. What I have sent to you. Ankit, sir.
Okay, fine.
Sir, yes, sir. Yes, sir.
Dear participants, please wait. Due to some technical problem, just within a few minutes, SAR will start. Angit Krishna has joined now. SAR will share this screen.
Yeah, I've shared my screen again.
Yes, sir.
Is it visible now?
No, sir. No, no, not yet.
Okay, let me do one thing. I'll again once again rejoin. Is it now? Can you see my screen now?
Sir, no, sir, it is not visible, sir.
I don't know. I mean, can you just give me access for?
Sir, actually,
ah,
sir, it is given access for you, sir. Sir, whenever if
Okay.
you click present now, you have
Huh?
to give a window. What you are giving, sir, a entire screen, a window.
I'm giving entire screen.
No, sir, you can just give a window. You open your PPT and you just
Okay.
click the a window. That is sufficient. Sir.
That window didn't work at that time. That's why I had to go for full screen.
Now it is okay, sir.
Just let me know if
You please
it's
check, sir.
visible. No, actually,
Right,
the
sir,
present now gets grayed out when I log in.
Uh-huh. But the access
Yeah,
is given
it's
for
not
you, sir.
allowing me
No
to
problem,
present.
sir. Sir, can we do one thing, sir? Can you just share the PPT so that we will share from our computer?
Yeah, sure. No problem.
Right, sir.
1 second.
There's some technical problem from the resource person side. Just wait for some time. And meanwhile, don't mute as unmute your video and audio.
Hello, sir. Excuse me, sir.
Sir, tell me, sir. Tell me, sir.
Actually, we are deposit your assignment. Can you share the answer sheet?
Sure, sir. At the evening we will share, sir. No issues, sir.
Okay, okay, and okay, okay.
No problem, sir. No problem.
Deposit your assignment. Can you share the answer sheet?
Sure, sir. At the evening we will share, sir. No issues.
Okay, okay, and okay.
No problem, sir. No problem. Sir, excuse me, Ankit, sir. Any help from our side, sir? Sir, excuse me, Ankit, sir. Any help from our side, sir? So, dear participants, please hold on. We are sorting it out. Due to some technical issue, we are sorting it out. Please hold on. We'll come back soon. Thank you. Dear participants, please hold on. We are sorting it out. Due to some technical issue, we are sorting it out. Please hold on. We'll come back soon. Thank you.
Sir, due to some technical problems, we need some time, and within a few minutes, within 5 minutes, the session will start. In meantime, any participants want to give a feedback regarding the morning inaugural session and the technical session, technical address, keynote address. So kindly, the participant can unmute and you can share your feedbacks.
Are you able to see my screen now?
Yeah, it is there, sir, but your presentation is not visible.
My presentation is not. I've already shared my presentation as well. Now, can you see?
No, sir.
Now?
No, sir. Sir, can you share the PPT to
I
our
have already done
coordinator?
that. I've already shared it to the
Okay,
HOD.
okay.
Can you just check once?
Okay, sir. Okay. Okay, sir. Okay.
Sir, just let me know if you're able to see this.
Yes, sir. Yes, sir. Please proceed, sir.
Are you able to see the presentation? Sir, just let me know if you're able to see this.
No, sir. Actually, you are joined with the new ID, I think, sir.
No, see, my email
Let
ID
us
is
see
not
it.
Gmail, so it's a government email ID, so I will not be able to join with that.
Oh, okay, 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 sir. But we can see you the image like a CMK Bangalore.
Okay, okay,
But we cannot see the presentations. Yes, sir.
okay, fine, right. Is it possible that you can enable the presentation? This one?
Yes, sir. Yes, sir. Yes, sir.
Can you
Yes,
do
sir.
that?
Yes, sir. Just
Yeah.
now you yes, sir. Just now you have shared, no? Our coordinator will share the PPT, sir, so that you can present your presentation.
Okay, fine.
Yes.
Hello? Yes, sir.
Excuse me, sir. Meantime, any participants want to share their feedback regarding morning keynote address and the first session? You can unmute and you can share your feedback, sir. And the participants, please wait. We are working on the technical part. Within few minutes, the session will start.
SV Colleges, Tirupati. +8,000 students, 400+ faculty, 3,000+ placements, 100+ companies. Green campus with latest infrastructure. Industry institute collaborations. Techno and cultural fests. Ranked among top engineering colleges in the state, SV Engineering College for Women is now SVEC with co-education. SV Colleges, Tirupati. SV Colleges, Tirupati.
Ankit sir, we are getting
Sir, we are getting
8,000+ students,
Ankit sir, we are getting your
400+
presentation.
faculty, 3,000+.
Sir, Angit sir, we can able to see your presentation, sir. You can proceed, sir. Yes, sir. We are seeing your presentation, sir. Go for full screen, sir.
Yeah.
Yes, sir.
Full screen, shall I go?
Yes, sir. Go for slideshow, sir, so that it will be big. Sir.
Now is it visible?
Yes, sir. Yes, sir.
Really sorry, we had to change the computer. There was some issue with the computer.
Okay. Thank you, sir.
Once again, extremely I'm apologetic for this sort of issue. Really, please don't curse me because I know it's afternoon and we've had good lunch. So anyway, let me, without any much further delay, let me start my presentation. This is a presentation I gave a few weeks ago in a similar platform at your college. Thank you very much again for contacting me. And this time I decided to go with a slightly, not very different, an additional focus on the deposition of carbon nanotubes and diamond-like carbon. So this has been a kind of the, now graphene is in thing, but then on a production scale, on a mass production scale, CNT and DLC is now actually in the forefront than graphene. And more so the applications that CNT and DLC have promised is a lot. And DLC is now used in so many domains, right from the high performance car engines to, let's say, even a tiny thing as screw or even machine tools. So that being the case, I have decided that these are the two things which we work in our laboratory here. And I thought that it would be ideal if I'm able to share with you my secret recipe of how to synthesize CNT and DLC. So shall I start with my presentation?
Yes, sir. Please carry on, sir. Please.
Thank you very much. So I'll be going with the what is surface coatings, some sort of what problems, applications, then why nano coatings are required, different technologies, and what we do, what sort of work that we do, especially with respect to DLC and CNT. So I would like to focus in this. And first of all, what is a coating? So if you apply any sort of material to a surface, which gives you some sort of a good property, that is a coating. And it's as simple as that. Any thin material which is thinner than the substrate size would be a coating. And coating forms a large part of a subject called as surface engineering. So surface engineering is basically a kind of a science which deals with modification of surfaces in order to achieve a particular sort of chemistry or to achieve a particular sort of physical property or some sort of a mechanical property which is essential for our final application. So the whole goal of surface engineering is modification of surface. So let's say if you want to make a surface quite smooth in order to improve the coefficient of friction. So that is one sort of property. So that can be used in bearings. Let's say you want to do a laser sort of an etching to get hydrophobicity. So that is another kind of property that you would be achieving using lasers etching. Or if you want to use plasma and bring about small modifications so that you can have some sort of cellular growth happening on the surface of a material. So that is another kind of modification. So basically you're in all these three cases, you're modifying the surface, and hence the whole subject being defined as surface engineering. So what advantages are we talking about? And what you're talking about is improved corrosion resistance, improved oxidation or sulfidation resistance, improved wear resistance, reduced frictional energy losses, improved mechanical properties, or let's say you are enhancing the or delaying rather the fatigue or toughness, improving the electronic properties. Let's say if you're able to engineer a very good band gap material using thin films, and that's something very advantageous. Thermal insulation can be given and improved aesthetic appearance. Why does the surface actually damage? And that is because essentially that we expose it to various kind of environments, maybe chemicals, thermal, environmental, and mechanical. You end up using, let me take an example of a race car, right? A Formula One car. So what happens in a Formula One car is that your engine is a very high performance engine. The heat that is generated is very high. So let's say the engine piston rings have to be coated with some sort of a low coefficient of friction. At the same time, it should be able to withstand a lot of heat. So that is one way to have that. Then there is also a lot of wear and tear in parts. So if you have seen the 50-lap race, you will find out that a lot of parts and a lot of components are being changed on an F1 race. And that is because you have wear, you have abrasion, you have friction damages, you change a lot of parts there. And then sometimes if you are looking at, there are certain that happens in rain. Okay, and when it happens in rain, then you have a problem of water a lot of parts of your chassis or your wheels between your braking and your drums. So these are other issues that you will have problems with. So all these things can be sorted by coatings. And always, if you see that the first sort of coatings that have always occurred is for either military or for aerospace or for such sort of high performance races where you actually need a lot of coatings, which will make a machine quite smoother and lasts longer. In fact, even in cycling races today, a lot of use of graphene material for lubricant on chains is being used. So they spray a graphene-based solution on the chain, leave it for 4 hours, and then they keep rotating the cycle for about an hour, so that the whole thing, the solution drips inside the sprockets, both in the major bracket as well as in the rear wheel sprocket. So that way it becomes a low coefficient of friction. And what way does it help? So basically in a race, they say that even if you are able to conserve 5 watts of energy, there's a good possibility that you will be in let's say if you are in top 50 or 60, you can go to within top 15. So that's how important a 5-watt drag that you're able to save. So which are all the industries and what are the applications essentially? So if you see here, you can see that in aeronautics, you can use in turbine blades, combustion chamber, nozzle guide vanes. In a lot of agricultural machines, you can have this. And then chemical and petroleum, you have a lot of reaction vessels, impellers, screw flights. Even in IC engines, you use it in piston rings, chamber, crankshaft, gudgeon pins. And then in medical, there's a lot of work that goes on body implants. And then you have textile industry of thread guides, winding spindles, flattening rolls. And even there are certain guideways which use this. And transports also, as I told you, where all it is used. So there are a lot of places where coatings are useful. And this is one small slide which shows you the different kinds of coating and the different regimes it is used. So just to give you one example, in each is like welding, which is slightly thicker in nature, is used in essentially in ship repairs. When you are on the sea, you weld, take out material there, and then you apply it. Thermal spraying is used very prevalent in aerospace turbine blades. And electroless plating is used in a lot of automobile sectors today. Even in your old grade watch plating, electroplating is used. Even in aerospace sector for doing a bond coat, like platinum aluminide, people use electroplating. Then comes the CVD system. CVD is used for making a lot of organic and metal organic depositions, especially for semiconductor applications. And so is a physical vapor deposition used for machine tools or cutting tools, as well as in a lot of aesthetic and also in semiconductor, wherein you have to make or MEMS devices where you have to have a platinum deposition or say nickel deposition for making some sort of temperature sensors. And then you have ion implanting. Ion implanting is now very much synonymous with physical vapor deposition, wherein you bombard certain ions. There are different various mechanisms for that. You can do E-beam evaporation as well, or E-beam bombardment, and that is used essentially in semiconductor industries. Then there is thermochemical diffusion, and Well, it's a very old graph. So thermochemical diffusion not only is in the sub-micron domain, but it also now goes up to micron domain as well. So what are nanocoatings? So nanocoatings are the coating that are produced by usage of some components at nanoscale to obtain certain desired properties. You can make crystalline coatings. You can handle individual layer thicknesses. You can change the grain size, grain boundaries, play with it, and then create an interface which will then impact your final application. You can try adding a defect, or you can try removing a defect, which is very, very useful in making N-type or B-type semiconductor systems. And then you can make a coating and make it chemically inert, physically strong sort of things. And you can actually make certain coatings which are kind of super coatings, which is not typically found in our conventional day-to-day life. So here is a small difference. One is a micron scale structure, one is a nano scale structure here. So I wouldn't go much with high contact tension. Today, you can achieve a lot of, though contact tension is reduced, you can improve your water repellence effect. You can also make hydrophilic in nature, and then moisture can penetrate housing because you'll still have certain gaps. Whereas in nano coating, it is atomic bonding or molecular bonding, and hence it's minimized. Minimize is actually an understatement. It's almost eliminated. Surface roughness, yes, you can reduce not only to 1 nanometer, it can even become a few angstroms. And conventional coating is slightly thicker. It goes up to even 150 micrometers in aerospace applications. And then you have the improved properties of conventional coating fields now. So electroplating, we'll go with the oldest and time-tested one, that what is an electroplating. So electroplating is one process wherein you have a cathode and you put it in a bath. And then, as you know, there is solution wherein the workpiece is plated with other metal through a water-based electrolytic solution. So the metal ions are basically transferred from, and they are deposited onto a cathode. So that exactly happens. So it dissociates at the anode and then it goes and attaches itself to the cathode. So you can do a lot of things. You can do a variety of shapes. The only drawback is that the disposal of electroplating is a solution after it gets bad is very, very hazardous. You can do it on complex shapes, but again, when you do it on complex shapes, you actually have to sacrifice uniformity of code. So as you know, that hexavalent chrome plating is now being banned in the country. So then comes the next generation plasma enhanced chemical vapor deposition. Now this is important for our talk today because when I talk about deposition of DLC and deposition of CNT, it is going to be using plasma enhanced chemical vapor deposition. So let's talk about what is CVD. So CVD, as I told before, is used in deposition of non-metallic and metal organic films. And you can do several kind of coatings, let's say optical, super hard coating, protection, aesthetic, are all usually deposited using CVD. So when I say gold color on watches here, it doesn't really mean you coat titanium nitride or gold. There are certain chlorides which you can use, gold chlorides or some sort of chlorides which is used. But of course, nowadays people have resorted to titanium nitride, which is used, deposited using PVD. So this is something which I've explained today, and that would be, first you have a chamber. So any CVD chamber for that matter, unless it's atmospheric pressure, would be in vacuum. You extract air from the chamber to the order of 10 to the power of -6 millibar and above. using either a cryogenic pump or you would use a turbomolecular pump, which is backed by a roughing pump. So when you use a roughing pump, then it kickstarts your turbomolecular pump, and in turn, the turbomolecular pump can achieve very high vacuum. So once you achieve very high vacuum, you evacuate all the gases and including dust. So let's say if your coating thickness is about 500 nanometer and you have a dust particle of about 2 micrometers, then it's not going to serve the purpose. And that's why you should go to very high vacuum. And then later on, you have a plasma source. The plasma source for a PECVD is either a pulse DC, an RF, or a microwave source. So you use a pulse source and plasma source, and then you generate plasma when you inlet certain process gases. With that, what happens is that the gas enters into this vacuum chamber, and when the plasma is switched on, the gas starts dissociating. There is a chemical reaction which occurs, there is a dissociation that occurs, and then slowly these things start adhering onto the surface of the substrate. So one by one, they start adhering onto the substrate surface, and then they have a molecular binding in nature, and that's how you start depositing the material that you wish to do using a CVD process. Atomic layer deposition is a more finely controlled chemical vapor deposition, and it actually offers a more precise control in terms of deposition, as it goes down to a few angstroms to a few hundred nanometers with much precision and very good uniformity. So the difference here is you would be using a lot of liquid-based precursors, which is then vaporized, and then you would be doing it. Of course, there are different machines having different setups, but technically speaking, atomic layer deposition, as the name states, that it is used for very, very low thickness deposition and is very useful in a lot of semiconductor applications. Now, physical vapor deposition. So all the cutting tools, metal-based ceramics, metals for temperature sensors, or maybe chromium for some sort of coating for protection, aluminum for mirror applications, are all deposited using physical vapor deposition technique. So basically, one very famous methodology of physical vapor deposition is magnetron sputtering system. So basically, you have a target, and what happens is you put in some sort of a gas inside. The gas is ionized, and it bombards the target. The target etches out material, and this etching out of material in very, very small scale is called as sputter off phenomenon, and this sputtered off material falls on the surface of the place where you wish to coat, and then that happens to be a sputtered process PVD. As you see, the applications on the slide is for hard coating, wear resistance coating, corrosion coating, and also for optical coating. So the principle of coating is something which I've already explained, is that you actually kind of try to eject material from a surface using some means possible. When you eject that material, that ejection of these sort of atoms is called as the sputtered atoms, and the whole process is called as sputtering. So this is a place for how sputter yield is. Basically, we don't have to dwell too much in this presentation, as it's just introductory in nature. But anyway, it's a good thing to know that it is based on the energy of the incident ions, the mass of the entire ions and the target atoms, the binding energy of the atoms in that solid target, and the incident angle of the ions. And this you will be able to even simulate using some sort of a either a molecular dynamic simulation or some sort of Monte Carlo simulations can be used to find out the sputtering. So the schematic is also pretty much similar to PCVD, or I should say that they are anyway a sort of vacuum system here. Only thing is the difference in the plasma source. So there you were using an additional plasma source of microwave. Here you would use DC. So that's the only difference. The rest, both the plasmas are going to be the same. And you use specifically argon. Maybe you can use oxygen for creating an oxide and the nitrogen for creating a nitride. So this is reactive sputtering, but argon becomes your principal gas for letting into chamber for creating a sputtering reaction. These are the two PVDs and PCVD that we have in CMTI. We will come back to that later. And as you see on the screen, our PCVD is essentially set to make only carbonaceous materials, essentially DLC and CMTs. Pulse laser deposition is also kind of a typical system wherein instead of using a gas and then ionizing the gas, you would rather use a laser. The laser would fall on a substrate and then it would remove material, and that actually gets coated on your on the material in which you wish to coat. So basically you have a laser beam which hits on a target carousel. The carousel is something which is rotating and is either you can have the laser beam at an angle or you can have the target at an angle, and which removes the material from the target and then it deposits on the substrate intended to be deposited. So let me talk about some pros and cons of the CVD process here. So one is that you can achieve very high coating hardness, good addition, and good thickness of coating, a decent thickness of coating. But sometimes the CVD process is a high temperature process, and this could cause some sort of a thermal expansion and would end up in peel off of material. Limited range of materials can be coated. You will have to sit and work out a lot on this. And there are environment process, concerns about the process gas which is being removed from the chamber or exhausted from the chamber. And similarly for the PVD process would be, it also has excellent process control, low deposition temperature. You can create dense and adherent coatings. You can also make some sort of stoichiometry can be handled. So you can have, let's say if you have a TIN coating, you can play around with the titanium content or the nitrogen content in the titanium nitride, and then you can get your own stoichiometry for any application possible. So yes, as any other vacuum system, vacuum processes are slightly having a high capital cost. You have a limited component size. Of course, now you can go to at least a meter or two these days. Coating rates are literally low. When I say literally low, when you're coating, depositing titanium nitride or any sort of ceramics, then the deposition rate lowers. And the time to coat is little longer. So which means to say that poor throwing power, you can say. You need to bias, but it's pretty much the same because it depends on the density of your target material. So as you recall that slide from the sputter yield, so it also depends on that, how much time it takes to deposit. So what are the good things about these sort of nano coatings? So good things are that you can have very controlled deposition from 0.5 angstroms or even lower to about 5 micrometer. You can engineer your film to what hardness you wish to. You can give a better wear resistance. You can define your optical properties better. Right from your sunglasses to the anti-glare glasses that you wear today, all are having nano coatings. You have very good surface addition, and it is very much environment and operator friendly. What are the bad things is that you need to have subject knowledge, and you really have to be very good with the basics, understand the chemistry of it, understand the physics of it. So when we put it in an industry perspective, you need to have somebody who's not only skilled but who's also suitably knowledgeable in this field. So usually you will find that a lathe machine or a milling machine is operated by either an ITI fellow or maximum a diploma person. But here you need to have a good, well-experienced person in this regard. You can't deposit really high thickness films, otherwise the film tends to peel off because of the stresses that gets induced in the film. So this is another technical reality of this. So what is the ugly part of it is that initial investment is very, very expensive. You require a clean room. Maintaining a clean room is a very, very tough task. And you have to give 24-hour power, 24-hour current, I mean, water chilling. So all these things are required for this. And then scalability is certainly an issue when it comes to deposition techniques, such as the pulse laser deposition. So that scaling is quite a challenge. So far, is this okay? So do you have any questions at the moment? I can probably take one or two, not more than two.
Okay, sir. I request our participants, is there any question? You can unmute and you can.
I would rather request you to just put in a chat here then so that I can just answer.
Yes, sir. Yes, sir. The chat is there, sir, but we are not finding any questions.
Okay, fine. In that case, I will just continue on with the presentation.
Yes, sir. Yes.
Sir, good afternoon, sir. Myself, Kuldeep.
Yeah, please tell me, sir.
Baba Saheb Bhimrao Ambedkar University, Lucknow, UP, India.
Very nice.
Sir, I have one. Sir, I have one query. We use the CVD technique to synthesis of the fabrication of the thin film purpose.
Sir, if you don't mind, can you put it on chat because your voice is breaking? Can you just put it on chat? I'll certainly ask you.
Okay, sir. Okay, thanks.
Well, I am Dr. Dilip Kumar Biswal. I'm very sorry. I do not work on this subject, so I would not be of any use to you in this area of yours. So I really do not know what that coating is. So I don't want to give something wrong information, which would hamper your research.
Sir, yes, sir. You can proceed, sir. I think no questions.
Yeah. I was just waiting for the question from the gentleman from Lucknow.
Okay.
Can graphene and CNT can be synthesized together? When you say synthesized together during the same time, possibly not, because you use two different kind of processes. You will try ending up having some sort of amorphous carbon in either of the processes. So not exactly you can't synthesize at the same time. But can you use the same chamber? Probably yes, you can. So what are the long pipes like absorber tubes? There are a lot of coatings for that. There are, you have paint-based coatings, And then I am myself working on some sort of DLC coatings with certain modifications for solar absorber. But yes, there are a lot of paint coatings that people use, which I do not do anyway. Can we use CVD techniques for powdered nanomaterial synthesis? Well, there is a technique where you use a pressured chamber with which you can actually deposit powdered nanomaterial. It's very similar to a CVD technique, but not exactly a CVD system, but yes, quite similar to that. So you have a pressurized chamber wherein you do that. Dr. Dilip Kumar Biswal, I'm really sorry. I do not know what this coating is. I wish I could have been of more help to you. I'm really sorry about it. Right, there are quite a few questions. Let me continue it so that I present on time, and I will again come back to questions in the next session again.
Yes, sir. Yes, sir. You can please proceed.
So let me continue with the thermal and E-beam evaporation, which is also part of a PVD process. As simple as it is, you heat something, the material melts and gets deposited. Now, this is thermal evaporation material. Thermal evaporation is just like heating water in the house in a vessel, or in simple terms, let's say you have an incandescent bulb, you have a tungsten filament. In case if I put some sort of gold or copper inside the tungsten filament, it has lower melting point than the filament, and it would immediately evaporate, and then it would start depositing everywhere. So that's basically thermal evaporation. And E-beam is just, instead of you using heat, you would actually use an electron beam gun. And then instead of having a thick material, you would actually use some sort of a crystal form of material or a powder form of material, and then you would use the electron beam gun in order to evaporate the material. So evaporation has very high deposition rates. E-beam evaporation, you can control, you can do anywhere from a semiconductor process of about a few angstroms, and you can even do aerospace turbine blades, single crystal columnar growth coatings using the evaporation process. So that's possible with that. Thermal evaporation is slightly, it doesn't have great addition, thermal evaporation, as compared to E-beam evaporation, but both are line of sight coatings, which means that if you have an object coming in between, then it's going to coat the object and not the thing which is behind it. Something like a solar eclipse, lunar eclipse concept. Yes, if I'm correct. So also, it depends on the vapor pressures of different metals. Sometimes you'll have to keep, but then again, you have to keep your chamber in vacuum, and that would be nice in order to get a very good uniform coatings with low contamination in this process as well. So comparison is that when I say condensation, it's not literally condensation, it's just movement of vapor, because it's anyway an atomic scale from one place to another place. And here it's by chemical reaction on CVD. And then there is material that is introduced onto the substrate in solid form. Here it's usually in gaseous form or liquid, which is then throttled as a gas. Atoms are moving physically and depositing on substrate. Here the gaseous molecule react with the substrate. Of course, it does ionize and then it does liquid. So at the end, it's something somewhat similar. And then PVD is low temperature. Well, you can even go to very high temperature, and CVD also uses extremely high temperature. The materials are more important here. You would rather do more metallic content on PVD, non-metallic content on CVD. That's something. And the coating thicknesses, that's, if you keep with respect to E-beam and thermal evaporation, yes, you can go to high thickness coatings, whereas CVD would get slightly lower thicknesses. I wouldn't say low capital cost is something when you use a furnace heaters, and that would be quite cheaper. An atmospheric coating would be really low cost. whereas a system where you require vacuum would be a high cost system. So this is a process comparison. Well, I have already given you the entire chart in the first slide. Well, today people go with a lot of technological advances. So I'll just put materials in perspective. Thermal evaporation is used for low melting point materials, E-beam for both metal and dielectrics. A lot of people do tantalum pentoxide, silicon dioxide for semiconductor applications. Can even do some things like Cockrolly or any M. Crowley methodologies in E-beam evaporation for aerospace coatings. Sputtering is used for both metals and dielectrics, nitrates, oxide coatings, PCVD. Dielectrics, if you're doing SiO2 or SiN, or even you can do graphene, carbon nanotubes, so on and so forth. And LPCVD would be mainly dielectrics. Thermal spray is another way of you heat up a spray gun and then you accelerate a material and then you melt a material that passes through the spray gun and then you coat it on substrate. Substrate is not usually molten. It's basically only the powder or the wire that you would feed. The feedstock would actually be molten and then you would do it. So you can either use the energy source is either a flame, you can use an arc, you can use a plasma, you can combine oxygen fuel and then do this. Very high temperature can also be used for doing sort of thermal spray methods. So the classification is something like this. So process temperature is very high in plasma spraying, but it's just on the spot for doing a plasma spray message. HVOF or high velocity oxygen fuel is another kind of a spray-based coating system. Yes, it has use a very high velocity and high kinetic energy is used here for bonding. Noisy, and that would be with any spray coating technique. It's very noisy and you need to have a very separate chamber in order to undertake any sort of spray coating. These are the applications. You can use it for repairs, thermal barrier coatings for aerospace applications, corrosion, wear protection, hot gas, especially in hot gas corrosion is, yes, of course, in aircraft turbine blades, but also in oil and natural gas. So nano coatings at CMPA, we work with DLC. Just to give you an introduction is what is DLC. Okay, before I start with DLC, this would be kind of my last part in this. So I'll again give a break here. And then if you wish to have any sort of questions, you can ask me here. Another, again, 2 to 3 questions. So first question is rigid or flexible substrate? You can do both. I have done both using a PVD. I have deposited on a flexible substrate as just as simple as an OHP film, and rigid is something which we always do. So both can be done. You have any other questions you can put forth before I start with the next section?
Sir, one question is in the chat box, sir.
Yeah, I think I've already answered that.
No, the last one, I don't know which relates that. Rigid and the flexible substrate. That is the question, sir.
You can use both. I understand that. Can you use rigid or flexible substrate for a coating? I would say you can use both. We have done captain coating on a captain substrate which was flexible, coating on an OHP sheet which was flexible in nature, or cellulose acetate which was flexible in nature. Rigid is something we do it all the time. We have used silicon, we have used ceramics. You can use that.
Yes, sir. I think there is no question in the chat box, sir.
Right.
I request the participants, is there any question? You can unmute and you can ask directly to our resource person. Yes, sir. I think there is no question in the chat box. It seems no question, sir. You can proceed, sir.
Right, fine. proceed. So before I actually kind of end this session or go to the next part, so what I request all the participants to do is that CMD is organizing a survey with DSIR, Department of Scientific and Industrial Research, wherein we are trying to collate the entire nation's requirement for nanocoating. So for academics, it would be that if you don't have a place where you can code, you can actually, we can support you if you fill up the survey, and if your voice is heard, we will become a policy matter, will be taken up by DSIR, and we can start having some sort of central research facility wherein we can do some sort of pilot scale coating or a batch type production. So I request you to contribute to the country by filling up this survey. Many of them might have done who were in my previous presentation, but people who are not, this is new to them, please do fill up this survey. It would be a great benefit to the nanotechnology community per se. So right, I am going to return back to presenting. So these are the two things which we do, diamond like carbon and carbon nanotubes. So what is diamond like carbon? So diamond like carbon is something like you would actually make a sort of it's neither diamond, it's neither amorphous carbon, it's something in between, which means that it's not going to be as hard as diamond or as soft as carbon. The properties are going to like somewhere in between. Contains, and hence it contains both sp3 and sp2 hybridization. Typical value is between 18 to 22 GPa. Offers very good scratch, wear, and even optical IR optical properties, and also is a very good lubricant and has a low coefficient of friction. So typically, the DLC requires temperature anywhere between room and 400 degrees centigrade, and you need to use a hydrocarbon gas source, which is ionized. So at further temperatures, you would result in the yield of more harder crystalline diamond structures called as a nanocrystalline diamonds or the ultra nanocrystalline diamond. So how do you deposit DLC? Now this is the most important part of this presentation. And so you can choose a hydrocarbon gas, let's say methane, ethane, or acetylene, and introduce it in the chamber. Then you require a carrier gas or a dilution gas, hydrogen, helium, or argon. I mean, we prefer hydrogen. Methane as a hydrocarbon gas, either methane or acetylene. And what we would do is that we would try to combine these both together in the chamber and then try depositing DLC. So then you have the vacuum chamber in which you let in these gases. You can subject it to 200 degrees or 300 degrees, whichever temperature you like to do it, and then use sort of plasma using RF microwave or pulse DC. And then what would happen is you would ionize these gases and then you would start depositing. So is it as easy as I say, or does it seem? Yes, it is extremely easy to do that. However, you have to get your hydrocarbon to your dilution gas ratios quite correct. So these ratios depend on the type of system you have and the size of the system, what pressure can hold. So based on this, you will be able to do it with this. It's quite simple to deposit DLC. But conferring it, or I should say that to make it happen or to get it to a particular kind of hardness or to get to a particular kind of a hardness value or a crisp nature, that is when you really need to have a lot of knowledge on how the film is being formed. Applications is so that you have higher hardness coating, abrasion, scratch resistance, chemical corrosion, and optical coatings for neutrality imaging. These are some examples that we have done here, and we put it on surgical knife. This is cutting tool insert, also germanium wafers as IR optics. Next, we will go down to carbon nanotubes. And carbon nanotube is also another allotrope form of carbon. Single layer of graphite, when rolled into a tubular shape, forms a carbon nanotube. So let's say if you have a block of graphite and then you peel off one layer and then you start rolling, then it becomes carbon nanotube. And essentially available as single-walled and multi-walled nanotubes. It's something like rolling of these leaves to smoke. I mean, we call it here as BD, so it's very similar to that. You actually roll it. Not that I promote smoking. Smoking is certainly injurious to everybody's health, but just to think of it of how this whole thing gets rolled into a carbon nanotubes, that's one of the best analogies that I can give you. Types of CNTs, single-wall carbon nanotubes, dual-walled carbon nanotubes, and multi-walled carbon nanotubes. So making single-walled carbon nanotubes is very, very complex. You need very, very high temperatures, greater than 1100 degrees. Whereas multi-walled carbon nanotubes, you can start synthesizing even at temperatures at 550 degrees centigrade. And that's most commonly found and most easily produced carbon nanotubes. So what are the requirements that you need to synthesize carbon nanotubes? This is quite important. That first of all, you need to keep ready a temperature or a chamber, vacuum chamber, which can go up to temperatures greater than 500 degrees centigrade. Then you have something called as hydrocarbon gas, like either methane or acetylene or ethane, and then use dilution gas such as hydrogen, nitrogen, or ammonia in specific ratios again. So typically for growing CNTs, the ratios would be 1:3, that is hydrocarbon to dilution, 1:5, 1:8, 1:12, and so on. And as I already said, that multi-wall carbon nanotubes are more easily synthesized as per the procedure that I'm going to share. So the first and foremost thing is, all right, you will have to deposit a thin layer of a metal like either nickel, iron, or cobalt, preferably less than 10 nanometers. And this is called as the catalyst layer. And you deposit using a sputtering system. Then what you do is you take it out into from the PVD system and put it into a vacuum chamber, preferably a PECVD, and then you heat it to, let's say, about 500 degrees. You introduce hydrogen and ionize it using a plasma. What happens is that these metallic films start breaking, partially because of the different kind of the surface forces that act on the film. They start coalescing and then they start forming globules, and then they form very, very small islands. This formation of islands is called nucleation. And this is very important. This is the preparatory step to start depositing CNTs. So the better the nucleation is, the good quality CNTs you will be able to achieve. And here comes deposition. Now, once you have nucleated, the same thing is run. Now you anyway have hydrogen inside. You add either methane, ethane, or acetylene is also introduced in the chamber. The temperature is more or less maintained constant. And then you start introducing, you again ionize it using plasma, and then either using RF or microwave generator, and then allow the process to happen for 20 to 120 minutes. And then you will find that you have started developing or started synthesizing CNTs. So the major difference between carbon nanotubes and DLC's deposition is that the introduction of a metallic catalyst layer, which is then annealed. So otherwise, the process is very much similar, and also the change in the dilution ratios. So essentially, you will have more hydrocarbon gas when you want to deposit DLC, and far lesser hydrocarbon gas when you are depositing CNTs. So this is a growth model. Let's say if you have a kind of a metal, so if you have sprinkled a nanometal powder, it will be three-dimensional in nature, and over that, you will start growing the CNTs. Whereas if you have a thin film and it is flat, and then when you put in some sort of a carbon gas, it starts pushing the metal to the top and it forms the cap. So that is the tip growth model. So it moves, the metal moves up, and from there the carbon nanotube starts growing from top to the bottom. How does annealing look like? So this is how the image of annealing is. So you will form very, very small islands. On this is where you start growing carbon nanotubes. And this is how you start depositing CNTs. If you see, these are vertically aligned CNTs, cross section, and this is the top view of the CNTs. So properties. So single wall carbon nanotubes are specifically preferred for electronic applications, as it can switch properties between conductor, semiconductor, and even metallic based on the chirality. Single wall carbon nanotubes exhibit a phenomenon of ballistic conduction or a conductor along the wall and insulator across. So this is how the chiralities look like. So if you actually observe, see the edge termination. So it is zigzag in nature. See, this is zigzag. So hence this is zigzag. So anything which is not uniform is called as some chiral, which is undefined chiral. And if you see an armchair, this is a seat. Okay, and this is your arms of the chair. So this is called as the armchair configuration. So carbon nanotubes are more easily produced and multi-wall carbon nanotubes, and they are used for structural reinforcement, and which can make them tougher if you use it in 1% or 2% by weight. And sometimes they can be even used for improving conduction in a material. So these are the properties. This you should get it in any sort of literature, what sort of properties you have. And obviously these mark the tremendous so-called significant properties of the carbon nanotubes. And then characterization, I will, these are the essential characterization tools that you require is what I'm going to cover here. So there are many ways to do it. One is to find out the film topographies using AFM or atomic force microscopy, or the scanning electron microscopy. Crystal structure can be used using transmission electron microscope or grazing angle XRD. Hardness is using nanoindentation. Thickness is using spectroscopic ellipsometer. Qualitative analysis using Raman spectroscopy, and optical properties using IR spectroscopy. And hydrogen content in a film, you can use the Rutherford backscatter. So this is a SEM image of carbon nanotubes, which I have showed on screen, typically how it looks. Raman spectra for a DLC, you find out the ID by IG ratio. There are so many things. Based on the ratio, you can infer. And then nanoindentation is a typical hardness plot of how the hardness varies with respect to gas flow in our case here. This is an ellipsometry plot which shows you the uniformity of coating. An FTIR which shows you the transmission of, in this case, the wavelength is IR wavelength. So how does it transmit through a thin film or through a substrate? And this is finally, this is a Rutherford backscattering graph, which actually shows channeling, and you see which is the dip over here. So that's how Rutherford backscatter graph looks like. So with this, I actually end my presentation. If you have any questions, now I'm willing to take questions.
Thank you, sir. I think we are seeing in chat box one or two questions, sir. Shall I read, sir?
Wait, I can actually come and have a look at it.
Yes, sir.
Yes, so here you go. Right.
Yes. So the question, which synthesis process is good for industrial purpose for synthesis graphene in larger quantity?
Right. So there are, so if you want a continuous film, PCVD would be ideal. And then there are other sort of furnaces which are a kind of, again, a CVD based furnace that you get, which is useful for synthesizing graphene in larger quantity. And that's the only way to do it at the moment when you're talking about large quantity, of course. Otherwise, there is also one more methodology which you can do is that it's a chemical based method wherein you put in potassium sulfate and then you add some graphite flakes in it and then you leave it overnight and then you stir it in sulfuric acid for a while and then you start preparing multi-layer graphene. That is also one very good chemical method to synthesize graphene, and that is typically used for making some sort of a membrane for doing water filters. So thermal stability of nano coatings and maximum temperature it can withstand and duration of coating. Now that depends entirely on the type of coating you're doing. So let's say if you're doing M Crawley or where M stands for any coating, or let's say Co-Crawley coatings, it can withstand up to 1100 degree of cyclic oxidation testing. And that has to clear minimum many thousand cycles in order to prove that it can be used for aerospace. And what is the duration of coating? And that depends entirely on your process. So if you're using an E-beam evaporation, you can do it within a few hours, say 2 to 4 hours. And if you're looking at some sort of PVD or CVD thing, that you can't go to higher thicknesses more than 3 or 4 microns, which you can do in order for it to know how much temperature it will be able to withstand. What is the advantage of Raman spectroscopy over EDX? So Raman spectroscopy and EDX are very complementary techniques. Please, there is no advantage or disadvantage of either. Raman spectroscopy is very good to find out the sp3 content, the sp2 content, and you can find out the kind of the stoichiometry or the film that you have, whereas EDX is only elemental detection. It will give you, there is this material, there is element A, element B, element C, or element D. You actually need both in order to qualify a substance. So there is no particular advantage, you need to use both. Right.
Yes, sir. Yes, sir. Sir, I request all the participants, please refer feedback form link is displayed in the chat box. So it is, please fill it, it is for administrative purpose. Sir, I think there is no question in the chat box, sir. I request participant, if you have any questions, you can unmute yourself, you can ask your queries.
So what type of coating techniques to be used in polymer composites? Right, this is quite interesting. If you want to coat on a polymer composite is one aspect. If you want to make a composite using, then that's a different whole technique. So let's say if you are making a polymer composite, let's say carbon fiber or a glass reinforced fiber, wherein you have a resin, and then you have either glass fibers, then that's a whole different process altogether. So you make a layup and then you start doing it. But if you want to coat over a polymer composite, which we have done, you can use either PVD or CVD, it doesn't really matter. So we have used PVD for coating TIN on a sort of a PMMA based polymer composite. So that is possible. So what type of coating techniques? Yes, that is possible. In case of Raman spectroscopy, what do we understand from D band and G band? That's a lovely question. So, well, I do not work with Raman spectroscopy as such. But yes, you can find out the defect and G, okay, in carbon nanotubes or DLC, you can find out the graphitic content using G band, but not entirely true. And D is basically the defect band. The ratios of these two would actually give you how much sp3 content you have. So this is all I have the understanding of Raman, because that's all the Raman that I need for my experiments. But yes, for other materials, if you're talking about making pharmaceuticals, then this have a greater significance. In biological aspects, they do have a lot of significance, and that's a total different study entirely. So this is all I can give you a partial answer. I wouldn't like to tell something which is wrong. So that's about it.
Thank you, sir. Sir, shall we wind up, sir?
Sure. My last request would be, do fill up the survey which I've given you on the chat box. It would be really, really helpful for the academic community as well as the industrial community. There are a lot of people who have actually put forth their views, including very prominent industries have come forward to put in their views there. Your names will be kept, your views will be kept, or identities will be kept private. We will not release, only your views will be known. We will not reveal the name of the person as such. So this is something which I can assure. So please do go ahead and fill, and we are not going to track you with this.
Okay, sir. I request the participant once again, please fill the feedback link which is provided from CMTI Bangalore.
If you have no more questions, then I would like to thank.
Yes, sir. Let me finish it, sir. Sir.
Yes, sir. Please tell me, sir.
Okay. Let us wind up here, sir. Thank you for your excellent presentation, sir. You have given complete 360-degree information about nanocoating, sir. For example, you have started with surface engineering and application of in industries, different types of coatings like thermochemical and ion implanting, physical CVD, PVD, and all the principles and the magnetron sputtering system. So you have given almost all the domains you have touched in the nanocoating, sir. Thank you very much, sir. Thank you for your wonderful presentations.
Thank you very much for inviting me, sir. Thank you so much again.
Thank you, sir. I request all the participants, you can join tomorrow. The time is 9:45 to 10 with the same link. So I request all the participants once again, you can rejoin tomorrow's session. It starts from 10 o'clock. I request you please join before 10 o'clock, that is 9:45 a.m. to 10 a.m. Thank you, sir. Now we are going to, thank you very much, sir. Now today, for today's session, we are going to wind up now, and we will rejoin again tomorrow. Thank you for all the participants. Thank you, sir.